Our next speaker is Dave Blei from Columbia University. If you have anything to do with machine learning, you know who Dave Blei is. If you don't have anything to do with machine learning and you go to a machine learning conference, you will find that about 10% or so of the conference is about his PhD.
Okay. Thanks, Peter. I'm Dave from Columbia. I'm going to talk about some new work we've been doing for the last 6 months or so called Exponential Family Embeddings. It will relate to networks, and that we've been doing for the last week. So this really is, in the spirit of a workshop, I'd like to hear your feedback. And I understand that I'm between you and your glass of wine. And you should understand that you are between me and my glass of wine. Okay, so here's what this is about. In natural language processing, word embeddings have taken hold. All right, this is an idea. If you've heard of it, you know what they are. If you haven't heard of it, I can give you the sense in this slide. It's a machine learning method that ingests a large collection of language and discovers what's known as a distributed representation of words. In other words, it assigns each term in language to a vector. Here we have a plot of some of these vectors where distances between words appear to capture semantic similarity and can be used downstream in algorithms for classifying and parsing and doing various things with language that you might want to do. In this picture, I picked it for this workshop. So the archive, you all know the archive, Paul Ginsparg, who's the founder of the archive, he ran the word embeddings algorithm on the entire archive and all million and so articles. And there's this beautiful Google map of words in the archive, and you can search it and zoom in, and this is the area around graphs and things like that. And this is the output. So, you know, this is machine learning, the heuristic Wild West, ingest a bunch of language, spit out this, make pictures, do stuff. Everybody makes money. There are many variants of word embeddings out there. So the original work is from Yoshua Bengio. It's a very beautiful paper from 2003, and then this really has gathered momentum 10 years later with work that scales up word embeddings and applies them to massive data sets by Mikolov and colleagues, multiple papers. But each variant reflects the same main ideas. One, that words are placed in a low-dimensional latent space, and two, that a word's probability, and there's a probability model at play here, depends on its distance in this latent space to other words and its context. So what I wanted to do, this is work with my student Maya and postdoc Fran and Stefan, is generalize this idea to other types of data. The idea that word embeddings are doing cool things, interesting things, but what if we wanted to apply it to other kinds of data, like network data or other types of data? And what we did was the classical thing, use generalized linear models and exponential families. And with this new idea, exponential family embeddings, we can now take the word embedding spirit and apply it to examples like computational neuroscience data, shopping baskets and purchase behavior, recommender systems, and networks. The bigger picture here is that we're trying to take a statistical perspective on these ideas from neural nets that seem to work well, but are perhaps poorly understood. And just to be clear, we don't really understand this either. But we did generalize it to multiple types of data. Okay, so this picture, Peter Hoff might recognize it. We took some data from one of Peter Hoff's papers and reanalyzed it and embedded countries that are interacting with each other in a negative way using this exponential family embeddings. And this very same algorithm we can use to analyze zebrafish brains. So I'm not going to talk about that now, but they take zebrafish, baby zebrafish actually, and have them, they put them in, they as neuroscientists, put them in virtual reality environments and show them different things. I'll explain. It's actually very cool. Maybe it's more for wine talk, but okay, here's what happens, even though I'm not talking about zebrafish, because it's worth knowing. Zebrafish, baby zebrafish, you can image their entire nervous systems, okay? And so they take baby zebrafish, they paralyze them, they put them in this virtual reality environment, and then they measure when the zebrafish thinks it's flicking its tail left or right, and they simulate that in the virtual reality environment. So they're imaging the whole thing. So they're seeing what the zebrafish is sensing. And when the zebrafish thinks that he or she is, I don't even know, that applies. If they think that they're flicking their tail right, then they make the environment go right. If they think that they're going left, they make the environment go left. Anyway, and they're interested in understanding the brain, and so we have all this zebrafish brain activity data, and we're trying to analyze it. But I'm not going to talk about it. Grocery store shopping data, I'll talk about that later, where we have data of people shopping at a grocery store. Okay, so exponential family embeddings. So the goal in word embeddings is to discover useful representations of words. In exponential family embeddings, the goal is to discover a useful representation of whatever data it is you're trying to model. And the idea, it's very simple, is that we have observations, x1 through n, where each x is a vector, or a scalar in most of our cases. Now, here's just some examples of different types of data. In language, xi is a word at a certain position in the text, and it's an indicator vector. It's got size, number of terms in the vocabulary, and there's a single one somewhere there to indicate what word it is. In neuroscience, we have a neuron measured at a particular time. This is the zebrafish neuron, and we're measuring the zebrafish's activity level in that neuron at that time. In shopping behavior, I indexes D and B, which is an item. D is an item like walnuts, and B is an index of a particular basket. So if somebody bought walnuts among a bunch of other things, then XDB is however many walnuts they bought at that trip. In a network, which is what we're talking about in this workshop, I indexes a pair of nodes, S and D, and the value is an indicator whether or not there's an edge between those two nodes, S and D. Okay, so we're going to analyze networks at an edge level here. Okay, so there are basically three ingredients to an exponential family embedding. They are the context, a conditional exponential family, and what we call the embedding structure, or you might call it parameter sharing. And the idea, here is a graphical model. This is just a schematic of the different characters that play a role in the probability of an observation. The idea is that there's two latent variables for each data index, what we call an embedding, which I denoted there rho, and something called a context vector, which we're denoting alpha. The fact that there are two is important. That seems to be what makes word embeddings different from classical things like PCA and other types of factorization methods. And we model each data point conditioned on its context, which are the data points around it. So you can see I have xi as the data point that we're focusing on here, and then maybe there's that pointer. It doesn't matter. You can see me point. And then the context are the two observations on either side of x, okay, that are highlighted in red there. And you can see in this little picture what I'm trying to communicate with this picture is that the distribution of xi depends on its embedding, that's rho, that's lined up with xi vertically. The context vectors, alpha, of the context observations, which are the two red nodes next to the left and right of x. Okay? So that's the idea. The latent variables then interact in the conditional distribution of x, and how they interact depends on which indices are in its context and which data point we're trying to model. Okay, this is a complicated slide. Imagine, I'll just describe it with an example and then describe the general mathematics. So imagine you go to a vacation town and there's a deli there. Deli is like a grocery store in New York. And it only has 6 items. Okay? So the 6 items are jam, Skippy peanut butter, Smucker's natural peanut butter, soda, in this case it's Coke, sliced bread, and pizza. Customers that walk into this deli, they do one of two things. They buy pizza and soda, or they buy peanut butter, jam, and bread. Okay? But the nuance, it's not even a nuance, is that they're only going to buy one type of peanut butter, right? Peter might buy Smucker's, Carrie might buy Skippy. It's probably about right. In econometrics, when items are bought together, these are called complements. Okay, so bread and jam are obviously complements. Same with bread and peanut butter. The peanut butters are substitutes. Okay, you're not going to buy Skippy and Smucker's, that's redundant. You're going to buy one or the other. And what we want to do is capture this kind of purchase behavior. And what's cool, this is like a problem for economists to try to capture these notions in items. But what's cool is that this totally different idea of word embeddings in the neural net literature, I think can get at this. Okay, so let's keep going with this example. Each item now, these are the items or the data, so our data, just to be clear, is a bunch of, you all walk into this deli and you all buy something. Some of you buy pizza and soda, some of you buy Skippy bread and jam, some of you buy Smucker's bread and jam. And what we want to do is analyze that data and capture your purchase behavior. So each item is going to have two locations in this latent space, an embedding row and a context vector alpha. There's one for each item here. And this is the core idea. It's simple. The conditional probability of each item depends on its embedding and the context vectors of the other items in the basket. So in this case, the context is whatever else is in the basket. And the distribution of whether or not you bought jam, given all the other things that you bought in that basket, is going to come from, in this case, a Poisson, in general an exponential family. And its parameter is going to be the exponentiated dot product of the embedding of the item and the sum of the context embeddings of the other items in the basket. And sometimes we can average this over the dimension or whatever, but this is the idea. You take what we're conditioning on, we use the context vectors, and what we're modeling, we use the embedding. Okay? And
excuse me.
Yes.
So, is XPI the number of whatever?
Yeah. So in this case, XPI is the
or
number of times you bought things, right? And you can see immediately that we haven't totally veered away from the ad hocness of the neural network literature, because we are going to model XB conditioned on XBJ conditioned on XBI. All right, so we're going to be in the Wild West about that. Okay, but we're going to fit embeddings and context vectors to data from this deli under a loss function that's inspired by this distribution. Yeah.
If I think of this as a generative model, then how would I generate data from this?
You can't. So at the end, as future work, I want to think about this as a generative model. But I'll give you two phrases that might help us get there. But right now, this is not a generative model. And nor does it specify a generative model. So there is work, there's a book written about it, and a bunch of papers about when specifying conditional distributions, even though we don't have our hands on the corresponding joint, leads to a valid joint. And here, it doesn't. Okay, because what has to happen for that to be the case is that the way that this appears in this distribution needs to be its sufficient statistic in the way that it appears when you're modeling it itself. And that's not happening here precisely because of this difference between rho and alpha. But the difference between rho and alpha is also what's interesting about all this.
Why is rho I transpose? Is rho I transpose? Or
It's rho I, yeah, so rho and alpha, I should have mentioned this, are k vectors. There's some dimension in this latent space. So there should be parentheses here. And alpha is 2. And x is a scalar. Yeah?
You mean that in order for this to come from an actual distribution, there's some equation that the rows and alphas have to satisfy?
Right, and they don't satisfy it. Oh, so they may not satisfy it. Yes, that's true. Yep, that's true. Good point. Yep.
So you can't wait. Okay.
And it's not even just, it's more than that, actually, because you see, it's the way x enters in the equation that determines whether or not this corresponds to a valid joint, and this x above x might not be the sufficient statistic to the distribution of x, in which case I think we might be sunk. But we'll get to that at the end a little bit. Okay, so here's what happens when we run this algorithm. We find all the things that we were hoping to find about this vacation town deli. First, pizza and soda are never bought with bread, jam, and peanut butter, and vice versa. Okay, so the probability of buying them is very, very low. Bread, jam, and peanut butter are all bought together. Okay, the probability is high. But peanut butter 1 is never bought with peanut butter 2. So peanut butter 1 and 2 are here. Their context vectors are the red dots. I should have explained. Blue is embedding, red is context. Their context vectors are the red dots. And so if you have peanut butter 1 in your basket, you're not going to buy peanut butter 2. Okay, you can kind of look at the dot products to see this. Yeah?
So the blues are the rows and the reds are the alphas?
Yes, blues are the rows, reds are the alphas.
So one of these is sort of the outgoing effect on buying other things, and the other is the incoming effect of being bought with other things.
Precisely. Yep. But again, in the Wild West, we're modeling them all together, even though we shouldn't. Yep. Okay. Good. So that's the idea. So it's really can be explained with this vacation town deli. More generally, so like I said, there are these three ingredients. One is the context. Each data point I has a context, which is a set of indices. Okay, that's how we define it formally, of other data points. And so an exponential family embedding model models the conditional of xi given its context, x sub ci. In language, that context is the surrounding words. If you print out a stack of neural net word embedding papers, that's what you're going to learn. In neuroscience, the context is the activity of surrounding neurons. We take the neurons that are kind of physically nearby to a neuron in the zebrafish and model those as and declare those to be its context. In shopping, like I just mentioned, it's the other item counts in the same basket. And in a network, it's other edges on the two nodes. Okay, so if I have an edge, and that's going to be what I model, then I look at the other edges that emanate from those two nodes, and that's going to be the context in terms of determining the distribution of this edge. Okay, oh, and so there's a little animation. You can see the context changing, and it also reveals, except there's a mistake there, it also reveals that this is an issue, right? Here I'm conditioning on the red, here I'm generating the black, conditioning on the red, here I'm conditioning on the same thing I just generated.
When you chose, David, not for the context in networks, you just decided that would be the simplest thing to do.
Correct, that was last week. Yeah,
Okay.
I'm open to all other kinds of things. Yep, hoping to get feedback. Yeah.
Can you briefly explain why rho and alpha should be different? In other words, why, for instance, in the co-purchasing, we shouldn't view this as a symmetric relationship? Or what would go wrong if we assumed rho and alpha were the same and just...
I don't think you can capture the peanut butter example then, that the peanut butter is bought with bread and jam all the time, but not bought with other peanut butter. Because if the peanut butter is bought with bread and jam, then its rows are going to be close together. And if rho and alpha are the same, then you're going to buy two peanut butters together, but then you have too much peanut butter.
So the point is things are not necessarily bought with similar things.
Exactly.
Good. Thank
Yep. And your intuition was right before. It's this outgoing, incoming kind of the asymmetry of conditional probability. Okay, second piece clearly is a conditional exponential family. We have rho and alpha. They're indexed by I, right? By the index of the data, and they are used in the conditional of each data point. And here's our kind of general notation where we have a natural parameter that's a function of the context data and the context vectors for the context data and the embedding for the data that is being modeled. And this can be any exponential family. If you have count data, it's Poisson. If you have, I don't know why that's happening. Gaussian for reals, Bernoulli for binary, etc. Okay, and the idea is that the natural parameter combines the embeddings with the context vectors in the way I showed you in the Poisson case where the link function was exponent, but it's generally just a link function f. This is just like a generalized linear model. It is a generalized linear model. Okay? And this is what captures that an item's embedding helps determine its count, and its context vector helps determine the counts of other items. And this is the same asymmetry we're talking about. Okay, finally, the embedding structure. This determines how latent variables are shared across indices, and this is important. That when I buy peanut butter and when you buy peanut butter, we are using the same embedding vector. And this is how we learn things about whatever it is we're trying to learn about, like words or neurons or items or a node in a network. And so, here I have now X multiple shopping baskets, and I use the same latent variables even though the context is changing and the data point that I'm modeling is changing. Okay, and so this is again something that you find across the neural network literature, and this is how you would generalize it to this other kinds of data. Okay, so that's it, those three ingredients. And then we model each data point conditional on the others. We combine these ingredients in a pseudo-likelihood. I used to call this a pseudo-likelihood, but then Maya, my student, pointed out that we can't call it a pseudo-likelihood because there's no likelihood, right? This doesn't correspond to a joint. So then we started calling it a pseudo-non-likelihood, but that seemed wrong, so now I just put it in quotes. Okay, and here it is. It's the sum of all of these conditional probabilities. We can fit this with stochastic optimization. The exponential families that we're assuming simplify the gradients. Here's the gradient. I'm running out of time, so I'll just go quickly. And we haven't posted a paper yet, but when we do, you'll see that, if you read it, that this setup that we just described, which is really simple, helps us understand a lot of the tricks that are in the neural networks literature, like negative sampling and hierarchical softmax. They can all be cast as something like this exponential family embedding. Okay, so let me show you some examples. First, I'll show you some examples of a real grocery store. We took purchases of counts on shopping trips at a large grocery store. These are item categories, 478 of them. And the context is other items purchased in the same trip. The structure are the embeddings for each item are shared across trips. And the family is Poisson. And here is the picture of these 478 items laid out in two-dimensional space. And we can look, for example, we're going to look at this little cluster in the top left, and we're going to look at this little cluster in the top right. And the cluster in the top right is like baking ingredients that all get co-purchased. The cluster in the top left are things around taking care of babies.
So for this picture, you chose either just the rows or just the alphas.
Yes, there's a mystery here. Here we chose the alphas. And the rows did not lead to the same kind of interpretable structure, something we're still thinking about. Okay, and when you compare this kind of model to, in terms of predicting held-out purchases, so we take a test set and we try to predict held-out purchases, we see that versus things like exponential family PCA, which is the same talk but applied to PCA, and other kinds of ways of factorizing count data, that this performs better. Again, even though there's no formal generative model here. Okay, so now onto networks. Now it's getting close to wine. Like I mentioned, the data are edges. Okay, so we're going to take some data from one of Peter Hoff's papers, but then we're going to unfairly apply Peter Hoff's earlier model to this data, which is not a good model for this data. So there's 25 countries, and I guess Peter measured the negative activity between them. Is that right?
Which paper are we talking about?
It's this paper. It's a good. I'll just let that response lay. So the context, as I mentioned, are other edges that involve the same pair of nodes. So if this black edge is the node that we're modeling, then the context are the nodes emanating from the source and entering into the destination node. And here, the structure is a little bit more interesting than what I just described. Instead of every edge having its own embedding, we're going to give a row value to each node, and then we're going to just take the component-wise product of them and declare that to be the edge embedding, and similarly in the context sense. Okay? The family is Gaussian because apparently this data was transformed so that there was real valued items on the edges. And by the way, there were multiple realizations of these graphs, so that's where the sharing comes in here. Okay, so again, this is like a week old, but here is a picture of these countries. USA is not on here, it's like way far away. And this, now here's the mystery, these are the embeddings. Here, the context vectors didn't seem as interpretable, and again, this is something we need to think about. So what's the intuition here? Well, countries are close if they have similar interactions with the other countries. All right, so I am a typical American with an embarrassingly limited view of world politics. Although it's something I'm working on. But for example, I noticed that Great Britain, France, and Germany are all nearby. Okay. This is different. So like, let's say you were to just, we're trying to factorize nodes here. Let's say we were going to just factorize nodes using the state-of-the-art method or a state-of-the-art method. We might apply the latent space model, the famous latent space model, and you get something very different, right? Because this is not capturing the same thing. This is saying countries are close when they are likely linked together, but in this case, linked means by some kind of negative interaction. All right, so I don't want to read the tea leaves too much, but these are just different ways of embedding the countries. And I was planning on saying that even if Peter wasn't right in front of me. Okay, so good. Word embeddings have become a staple in natural language processing. What we try to do is distill the essential elements of word embeddings and generalize them to many settings, basically using familiar tricks from statistics like exponential families and generalized linear models. Compared to classical factorization, I didn't show you all the tables. In a real computer science talk, there would be lots and lots of tables. There's good performance on many data. So when we compare this to lots of different, to factor analysis and exponential family PCA across data sets, we get the same kind of results in the table that I showed you. And I think the preliminary results on networks are interesting. So, can we use a different objective? What do we know about this pseudo non-likelihood? Can we cast these ideas in a proper joint distribution? This is, the most non-Bayesian thing I've ever done, and it's upsetting. So, I would want there to be a joint distribution at play. I was hoping that we'd have these conditionally defined joint distributions, but that we don't. And so, two ideas. One idea, this was my student Rajesh Ranganath had this idea, was you could define a joint distribution that kind of just takes a finite number of steps of this conditional stuff, starting from scratch, and then try to analyze that. That could be one. Another is to simply take that objective function and call each term a factor in an undirected graphical model, and then that is a joint distribution. It's going to have a complicated normalizing constant. Would that change the essential analysis? I'm not sure. What are good priors and regularizers for the latent vectors? So we just were using L2 regularization, or a Gaussian prior, except there's no model. And would be interested in looking at things like sparse regularizers. And we're taking map estimates here. So we're just optimizing those vectors. But we could use other methods like variational inference or even MCMC. Would that help matters? And I'm interested to hear what you think. Thanks very much.
Are you doing the last sharing?
Well, I think I gave. We'll decide how many questions you can take before he has a glass of wine.
Ah, okay. So now I have to decide when everyone drinks wine? That's not good. Zubin.
So I want to drink wine very soon, but so part of the problem here is this disassortative or heterophilic structure, like in the negative interactions. But as you well know, there are variants of the mixed membership block model where, the little affinity matrix says that, how often things connect to other things can be bigger off the diagonal than on the diagonal, so that you're more likely to interact negatively with countries in the other group, and then you can try to infer those parameters too. I'm just wondering, does that not work as well, or, I mean, in the end, that's another kind of Poisson factorization, depending on which variant you use.
Yeah.
But
that's a good point. I hadn't thought of that.
Co-purchasing seems harder because it's more of a hypergraph, blah, blah, blah. People might go in with with latent variables about how many things they're going to buy that day or how much they can spend. But for the network thing, it's not obvious to me how much this adds.
Yeah, I'm not sure. So you're right. For even in the shopping case, you could imagine we could stick peanut butter in its own. Oh no, we have to stick both types of peanut butter in their own little communities, and then each type of peanut butter co-purchases with the bread jam community, but not with each other. So it'd be a little complicated. I'm not sure. Yeah, Zubin. But it's an interesting point. I hadn't made that connection.
So on this point about making a proper model of the product of the pseudo non-likelihoods, I'm just wondering whether it might be impossible because each of these terms has the data in it in the normalizer, so the normalizer might then depend. It might not be a single normalizer. It might actually depend on the data itself. So if you
yes, that's true. So it might not integrate.
Yeah.
Yeah, that's right. We'd have to think about it. You're right. Yep. Yeah. Yeah, Dan?
What seems helpful to me is the context structure, which, so in many of the network models, when you're deciding an edge, it's conditional on those representations. And so the representations of other nodes in the network that don't come into play. So this is different. So that seems interesting. But I'm wondering how you anticipate dealing with, say, Facebook when, say, two individuals each have 500 friends. Are you imagining a sum over 500 terms, or how would you have any?
I don't know. Yeah, you might want to think about a different type of context in that setting. Maybe you even learn weights on the friends or something like that, so that
I guess.
Or maybe there's even a mixture model underneath this. I mean, you know, we can play all the usual games.
Yeah, I guess, though, I think this is interesting because when I've looked recently at, say, movie rating, there are models that have come out that are not latent space type models and don't correspond to, or not latent variable models that do much better, and they seem to be taking into consideration context better. So I think the fact that your model does that is good.
Yeah, this works well with movie ratings. I didn't show you these results, but this does very well in movie ratings, actually in combination with kind of classical matrix factorization methods. So you have a user vector, user preferences, an item representation, and then you have the co-occurrence. You're like simultaneously modeling co-occurrence patterns and the asymmetry of those co-occurrence patterns, right? If you watched Empire Strikes Back, you're going to watch Return of the Jedi. You're not going to go watch Star Wars after that. Anyway, taking both pieces in a single objective function. But then both of your points, I mean, I was hopeful that we could put this into a real generative model, or at least a probability model, but it's true, if it doesn't integrate, then we're sunk. Or we have to not use probability models. Yeah. Oh, yeah. Go ahead, and then Peter.
So, people use similar models or have looked at similar models for part of speech tagging, given the words around the target predict the part of speech. Is that
yes, this is exactly that idea.
And they've found in part of speech tagging that you can get basically the same accuracy using a Markov model instead of just fully traditional. Have you noticed you get better representations when you add the two-sided context? So, substantially better than just having one-sided context?
I guess we haven't tried the one-sided context. And I went back to this slide because in his original paper, in Bengio's original paper, it is one-sided. It is a proper probability model because it's Markov. And yeah, that would be something we should look at, of course. And this paper basically is a one-sided model with a nonlinear term in it. And then what Mikolov did was make it a two-sided model and just throw out the neural network and just have linear terms. And that let him scale it up. Yeah, Peter.
Well, I just sort of making a frequentist comment, which is in some sense what you're trying to do is you have some joint distribution for these x's. I don't know what the hell they are. And you have this objective function, and now you have to take the expectation of that under that function, under that p.
Yeah.
And you want to find, what you'd like is the parameters which maximize that. And presumably the effects are coarse enough so that the parameter which corresponds to that is okay. On the other hand, of course, because you have a lot of parameters, it may well be that your estimates and so on bear little relation to the expectation given the past, and that may account for a lot of the not so good stuff. But at least, if you put it that way, then you, in principle, don't have to worry about whether there is
a formal model. Yeah, that's a good point. Yep.
Because you did kind of suggest that non-Bayesian meant nonsense, but there's also frequent stuff.
Yes.
All right, maybe we should.
Okay. Thanks.